Hello, everyone. I appreciate this opportunity to present today for this lunch seminar, the topic titled Opportunities and Benefits of Pinch Analyses in the Praxis. My name is Donald Olsen, and I work in the research group Thermal Energy Systems and Process Engineering, where we are actively involved in the applied research and application of pinch analyses. We are also members of Work Package 4 and Work Package 10 and several other work packages in the DeCarbCH project. The following points are going to be reviewed. To begin, I will provide a review of the pinch analyses and its fundamentals. Next, I'll provide some examples and demonstrate storage integration using the pinch software. Finally, I'll present some overall results related to the Swiss industry, followed by some research activities that we have been involved in. The motivation behind the promotion of pinch analysis in industry is best illustrated as shown here in this first slide. It is clear that process heat is a major proportion of the total energy use in Switzerland. By finding optimal ways to improve the energy efficiency in industry through heat recovery is key. However, there are several challenges in industrial energy optimization as shown on this next slide. The first is determining how energy efficient an industrial process is presently. The second is to understand what the energy demand is if the process was fully optimized. Thirdly is to understand how energy conversion units or renewable energies can be properly integrated. And finally, it is important to know how to determine the economic optimum for the trade-off between investment and operating cost and to determine how all this can be achieved. The key to getting these answers is process integration using pinch analyses. So what is energetic process integration? As noted in the first point, it offers another perspective on processes and how they behave energetically. Most important is the second point in that it provides a system-oriented method that allows an engineer to determine the optimal energy use and plant design under the condition of minimal cost. The third point more directly states energetic process integration is energy optimization based on a systematic method and avoids the more common trial and error approach. The most important tool used for energetic process integration is pinch analysis as described on the next slides. On this slide is shown the basis of pinch analyses, the composite curves. As shown here, it consists of two composite curves, a red and a blue curve representing the cooling demand and the heating demand of the entire system. They can be plotted and shifted relative to one another graphically to determine the amount of heat recovery possible within the system, indicated by the degree of overlap of the two curves. The amount of heat recovery corresponds to a particular minimum approach temperature, referred to as the delta T minimum, which exists at the most constrained point of the two curves, or pinched part of the system, more commonly called the pinch point. This delta T min is a fundamental design parameter for process integration. It relates the thermodynamic performance of the system to the economic performance as shown on the right side of this slide. As the delta T min is increased, investment cost goes down, but the operating costs will go up. By decreasing delta T min, the reverse happens. Investment cost increases, yet operating costs decrease. At a particular point, an optimum delta T min can be determined that minimizes both investment and operating cost. This optimum delta T min provides the targets and constraints for designing the energy efficiency measures. Benefits. Some of the benefits of pinch analyses are listed here. Using pinch analysis provides several important ones. The first is the holistic optimization involving plant design together with energy efficiency, utility systems, and of course, capital and operational expenditures. The results of this optimization is a strategic plan for energy efficiency measures and their associated cost benefit analyses. This is often overlooked benefit and that helps decision makers in the roadmap development for improving energy efficiency. Finally, results have shown the reduction of energy demand to be typically between 10% and 40%, depending on the type of process, ranging from the more mature, from an energetic perspective, of continuous processes over the last decades through to more recent work in non-continuous processes and batch processes of 40%. In relation to the benefits, the concrete results of the pinch analyses are as follows. Determination of the absolute energy savings potential is possible for both retrofit, which is the most common, and new plants. An optimized heat recovery and a utility system in terms of the heating demand supplied through such mediums such as steam or refrigeration for the cold, as well as renewable integration or energy conversion unit integration, etc. This includes the consideration of the correct integration of such systems, including energy integration units as well as renewable energy systems, as I mentioned. And finally, a catalog of measures with their cost-benefit analyses is directly available. Generally, the time taken to conduct an entire energy optimization project from beginning to implementation, including pinch analyses, is lengthy. In this case, you can see typically we've seen for full detailed pinch analyses an effort of between 3 and 6 months duration before it's ready to move to detailed engineering and implementation. This is largely due to the data extraction phase, which normally requires up to 70% of the project effort, and the difficulties in understanding the process energetically from a systematic perspective and concretely identifying the process requirements actually needed for conducting the pinch analyses and understanding the energetic behavior. The length of this phase directly impacts the costs of any energy optimization project based on pinch analyses. As shown here, having suitable software tool is necessary for the efficient completion of a pinch analysis project. It must be stated that properly defining the process requirements has the greatest influence on the heat recovery potential. This can be accelerated with tools such as the energy modeling tools based on standard spreadsheet-based approaches for balancing the mass and energy balance and doing the data extraction. This next slide relates to the support provided by the Swiss Federal Office of Energy here in Switzerland for pinch analyses as a backbone for the energy strategy development. Based on the experience obtained over the last 10 to 15 years, the Swiss Federal Office of Energy has defined 2 phases of a pinch analysis. As shown here, they consist of a rough pinch analysis and a detailed pinch analysis. The goals of each type listed here have the obvious primary difference being the level of accuracy between the 2 phases and, of course, the time involved. However, they have proved to be effective in promoting pinch analyses, and the Swiss Federal Office of Energy provides financial support for each of these phases, which are available on the Energie Schweiz website. Within our own research group, we have been fortunate to be selected by the Swiss Federal Office of Energy as the Process Integration Pinch Center to support and promote the application of pinch analyses in the Praxis. Our activities include the following is listed here: this pinch software development, which I'm going to demonstrate in a few moments, as well as the maintenance and continued support, some consulting and industry and engineering firms as well as providing continuing education courses and teaching, and as well as customized training courses and individual coaching. These activities help promote and advance the understanding of pinch analyses with the goal of increasing adoption of methods, especially among young engineers. Now, the pinch software, as noted in the previous slide, is one of the key activities of the center in terms of the development. The software provides an easy-to-use approach for the practical application of pinch analyses. As noted previously, without such a tool, pinch analysis would be very difficult to complete, given the challenge with increasing number of heating and cooling requirements. The software guides the engineer stepwise through the analyses and supports rapid evaluation of variants and scenarios. The Swiss Federal Office of Energy has supported the development of pinch to ensure the capability to support industry typically found in Switzerland. Now I'd like to switch to some examples that have been done here in Switzerland. And the first example is in Swiss industry, supported by the Swiss Federal Office of Energy, is showing on this slide the composite curves of a textile production process. The pinch analysis first assessed the potential for direct heat recovery, and what is typical of Swiss industry showing different operating cases was determined, in this case, summer and winter. The pinch analysis showed the heat recovery potential to be in winter approximately 1800 kilowatts, based on what is a typical number of streams of about 55. Now, it's shown on this slide is the analysis was extended later to include additional heating and cooling requirements that required the use of a storage system. This next example concerns the integration of a heat pump into a paint shop process. Now, paint shop processes are often seen in Switzerland as well as Western Europe in the mechanical production equipment processes. And the pinch analysis shown here enabled the practical and correct integration of a heat pump, as we see in the grand composite curve, represented by the evaporator and the condenser being placed properly relative to the pinch point. The associated savings and payback is also shown here that proved to be quite adequate for infrastructure projects. Next, we have an example from the mineral processing industry that has the characteristic of having substantial amount of waste heat at relatively high temperature. This is typical of such smelting type processes. As shown in the diagram, an organic ranking cycle was investigated as a suitable excess technology. However, due to the resulting poor efficiency of less than about 10%, it was not implemented. However, the capacity of a local district heating network could be expanded to use the excess heat. This final example is showing a process from the chemical industry. There's a well-studied batch process from England that illustrates the challenge of heat recovery in the batch processes due to the non-continuous behavior. The flow sheet shows the individual pieces of equipment and the associated heating and cooling requirements bound to each of the pieces of equipment on the left-hand side of this slide. The other graphics show the developed indirect source sink profiles graphic used to assist the engineer in completing conceptual design of a cost-effective storage system. Now, this graph is built on the heating and cooling demands bound to the time slice model that I had showed, that I'll be showing in the demonstration next. The result is shown on the right-hand side with the schema, showing a complicated schema simplified to 3 hydraulically decoupled stratified tanks. So I'm going to now switch to the pinch software to demonstrate this example. Now, here shown is the desktop of the pinch software, and we can see it's divided into several aspects, several views on the left-hand side, or a series, 2 explorers. The upper explorer, the project explorer, is the definition of the problem and configuration information to define the particular problem. And on the lower target explorer, we can see here we have the definition of different variants and scenarios for our results. In the middle section, we can see here is where we're going to have display of information for inputting data and outputting the information. The starting screen, splash screen, is shown here, just a simple diagram to help new users to understand what the basic process is that's involved. We've broken it out into 10 systematic steps, ranging from starting from the streams themselves or the heating and cooling demands definition through to the results, and finally detailed design step 10 and what's called heat exchanger networks. But the key first step and the most important part is defining the heating and cooling demands themselves, part of data extraction step, as I mentioned earlier. And here you can see the model is quite straightforward. Key to define is the temperatures that are actually needed in our process. In this case, feed preheat needs to be heated from 10 degrees to 60 degrees. That's the defined heating requirement for the process itself. Of course, we can then now calculate the change in enthalpy that will occur. And with that, given the fact that this is a time-dependent process, we need to define when those heating and cooling requirements will occur on average relative to the other heating and cooling demands. And we can see here we define that with a starting and a stop time. With those values, we have the ability to now create a Gantt chart as shown here on this equipment-wise repeat operation period, representing a relatively speaking static definition for the occurrence of those heating and cooling demands relative to each other as defined previously. And you can see this characteristic of a batch process that comes through is that we have heating and cooling requirements that exist on their own and not overlapping with other heating and cooling demands for direct heat recovery. There is a possibility to do so in around the distillation column, which would be something that should be investigated. However, with this time-dependent behavior where there's no overlap in most of the other heating and cooling requirements, this is an indication that storage, thermal energy storage, is an opportunity that could be used here to increase heat recovery. And now I'd like to now switch to how that looks. And in our model for indirect heat recovery, we can go ahead and in our target result configuration, using this selected process and the selected utilities, I can now add indirect heat recovery calculation object. And we can see here that we are able to immediately see the indirect source sink profile defined with with the maximum amount of heat recovery of almost 3.5 megawatt hours. However, it's quite a complex design, and we can simplify things and we can reduce the number of temperature levels needed in a particular storage tank. And we can do that by reducing it to 3 intermediate storages, which results in 4 temperature levels. And what does that mean? I can now open up the schema so we can take a look at how that model is shown. And we can see here the model shows a stratified tank with, well, these are the default temperatures that are defined by the indirect source sink profile. We also have laid out the cooling demands directly from the stream table, as well as the heating demands and the associated heat exchangers and their performance as they transfer heat to the intermediate loops bound to each heat storage, a heat storage being the temperature difference on particular temperature levels in the stratified tank. So this looks quite complicated, and this is something that has proved to be in industry difficult to control. So the nice thing about this design here is we're able to allow the user to simplify things. And we can see here, we can look at some of the demands and see which ones are most relevant. And we can see that we have quite a low amount of heat transfer capable with the heating, the reactant heating, as well as the product reheat, as well as the product cooling. And we can see that by removing those streams right from the calculation of the indirect source sink profile and the associated time-dependent behavior, we still have the same amount of 3 megawatt heat recovery, but our volume has decreased and the complexity of the design has been reduced. Now in this graph, we can see we have a graph representing a very simple payback calculation. How is that calculated? We can now go to another series of graphs, and we can see here now where the time slice model is now bound to the indirect source sink profile, which is plotting temperature versus the energy content of those streams. So we're bringing this behavior into the time-dependent behavior into the calculation to allow us to determine what's called a loading and unloading profile. And this loading unloading profile is in principle an idealized thermal Klein profile, which allows us to determine at what point the maximum volume for this stratified tank will be required when the tank is loaded with a particular temperature levels. With that information, we can of course calculate the volume and the mass of water and the volume of the tank, and using cost correlations, we can calculate the cost of the stratified tank, as well as given these heat exchangers defined on the intermediate loops, we know the area that is involved because we know the temperatures on each side of the heat exchanger, as well as the power or heat flow that's required. So we can calculate here a total area that we required, and using correlations, we can calculate here on the savings and cost table what the total cost will be for that storage unit with its heat exchangers. And of course, that can be amortized. And given that we have now used indirect heat recovery to increase our heating and our heat recovery through the storage tank, we are reducing our hot and our cold utility demands directly, both of them, and we can calculate the savings given the specific cost for each of those. And that results in the calculated payback that we saw here, in this case, just under around 3 years. Quite an optimistic value, but I think that makes sense when you look at the scheduling of the so many batch processes that were configured and the potential that's given of about 3 megawatts per batch. Now I'm going to switch back to the presentation to continue and conclude. So that was the example number 4 shown in the Pinch software, and there with other optimizations, we can see that we can reduce the complexity as well. I didn't get a chance to show that, but we have the ability to present the hydraulically decouple each of the designs so that we can have just 3 stratified tanks rather than 1 larger one. This next slide shows the economic energy efficiency potential using process integration. We've used comprehensive data analyses here to determine how large the remaining economic energy efficiency potential of Swiss industry is. The focus has been on economics, i.e. measures that companies should implement one way or another given their economic viability. First, we had evaluated in Switzerland the pinch analyses that have been conducted. Then the achievable energy savings were determined over the large number of potential additional processes that can be analyzed to be at least 3 terawatt hours per year. And the associated CO2 reduction was found to be a little more than 500,000 tons of CO2 per year. The net savings per ton of CO2 reduced is almost 400 Swiss francs per ton. So this is, in this case, a negative CO2 avoidance cost. In other words, it's going to be a profit. And as we can see here, what we conclude is process integration is by far the most effective method to save energy in industry. With the use of additional tools and methods, process integration can be applied in small and medium-sized enterprises given this value of 3 terawatt hours per year, and therefore the potential will be increased markedly in the future. On this next slide, I would like to move to the topic of applied research in relation to decarbonization. Process integration helps in the proper integration of energy conversion units, as I mentioned earlier, such as a heat pump, as a key technology for electrification. As noted here, the immediate challenge is that the vast majority of processes in Switzerland, in particular, are non-continuous, and storage must somehow be included together with a heat pump if we want to increase the potential. How to do this optimally together with a heat pump is a recent research topic of our group that extends the available pinch analysis tool, such as the ISSP shown previously, just for the indirect heat recovery aspect. The diagram here shows the non-continuous behavior of a cheese production plant together with the resulting ISSP. So here's the Gantt chart here showing the time-dependent behavior of each of the heating and cooling requirements over a 24-hour period. And here is the ISSP, resulting with the heat pump, condenser, and evaporator integrated into the ISSP as shown as a variant. That's one of the optimum solutions. Now on this slide, we see the main, there were several other variants, and we see the main variants found during the optimization technique. Conveniently, the system design, as well as the hydraulics, the key component sizes and costs are computed automatically. This allows a convenient display of profitability and complexity of each variant to be compared. This approach supports the engineer in making a decision of which design to include for further investigation and which to exclude. In this case, variant number 3 here, using only a heat pump design, is shown to be the most promising, primarily through the fact that the economic parameters and the savings are substantial, but the design using good engineering judgment is shown to be less complicated. For example, in variant 4, which is shown to be economically the best, and certainly better than just using indirect heat recovery through storage without heat pump integration. It improves it dramatically. Therefore, variant number 3 would be the one selected, and this is showing to be a powerful contribution to decarbonization in industry. On this final slide, I would like to highlight the role of process integration to the DeCarbCH project that we are involved in. Process integration is to be used as a basis in several aspects. The first is to enable the determination of energy demand profiles at the sector level, and then later at the company level. Work has already started on using pinch analyses projects completed in Switzerland to develop some sector profiles. For example, here on the right side, shown for the meat sector. Based on these profiles, the optimum integration and implementation of energy efficiency measures can be determined. More significantly, in relation to the DeCarbCH project, these profiles can be used for evaluation potential for renewable energies, as well as fuel substitution, negative emission technologies, and excess heat technologies. To do this, development of additional practical methods and tools along with decision support tools will be needed. In closing, I would like to summarize by stating that the process integration, and in particular pinch analyses, is key to optimizing industrial energy efficiency. This presentation has illustrated the opportunities and benefits of pinch analyses and focused on the practical application as well as the overlap to the DeCarbCH project. On this last point, I would like to conclude, and I thank you all for your time.